it's almost impossible to cover them all, but we will try. So it says a spring has a natural length of 20 centimeters and a 40 Newton force is required to stretch and hold the spring to a length of 30 centimeters. How much work is done stretching the spring? So there's a couple of formulas that you need to know. One of them is F equals KX. And if it is a reminder, forces in newtons, X is in meters, not centimeters. So this one, I don't really like this question because of that, but to stretch it from 20 centimeters to 30 centimeters would be an X value of, and it's because you're dividing both these by 100 to get it to meters. It's really 0.3 minus 0.2, which is 0.1 meters. And you're doing this because you need the K value, because that's what you need for the work problem. Okay, so F equals KX. The force is given as 40 newtons. There we go. So that's 40. Sorry if you can't see that. K times 0.1, you solve for K. K equals 400 newtons per meter. And that's kind of your physics problem, but when it wants to know how much work is being done to stretch the spring from, if we go back to 35 to 38 centimeters, that's where you need your calculus. So the mistake here is to think that these are the bounds of your integral. There's a couple of issues here. One, it has to be from the natural length. So it's really 35 minus 15, and then 38 minus 15 for your bounds. And I'm sorry, 20. Not 15, 20. So, and then similarly, it's in centimeters, not meters, because, in terms of springs, we don't think of them stretching very far, but there's actually big springs that exist in the world. So your work is the integral F dx, and F is your work function. So in this case, like it's F equals KX is the most common one that you might see. For that. So in your problem here, it's the integral 400x. This is your F dx. And then as I mentioned before, you're going from those units of integration here. 35 minus 20, 15.15, 38 minus 20, 18.18. Like this, and that's your work function. So that's a spring problem here. Do you want us to work this out, carry this out to the end?
No, that's fine. I can get past that. Thank you.
Okay. The next type of problem that you might see is like a cable pulling a bucket over some distance. So I can just work through that problem also to show that out.
Okay, sounds good.
So we have a cable that weighs 2 pounds per foot, and it's attached to a small bucket with coal that weighs 800 pounds. The bucket is initially at the bottom of a 500-foot mine shaft. So this is think of this as a pulley over the edge of a cliff. And this right here is 800 pounds. So you could have US units. Pounds already includes gravity. And then the distance here is 500 feet. And then they're saying that this rope, because there's 500 feet of rope, like there's this, you have to also consider the weight of the rope as you pull it, because the rope adds weight, but it's 2 pounds per foot. Okay.
Okay.
So basically, like at the bottom, like when this thing's at the very bottom, you're pulling, and this is, I think, a good way to think of it. You're pulling 800 plus the length of the rope, 500 times 2. So like you're pulling 1800 at the bottom, but at the top, when you get all the way to the top, you're no longer pulling the rope. You're just pulling, like when this thing gets all the way up there, you're just pulling the 800. So this 500 goes to 0 over the length of this 500 feet.
Okay.
Have you seen a problem like that in class?
We didn't do a lot of practice on work, which is why I wanted to review it here because we
Got it.
barely did any practice.
Got it. Got it. Okay. So the force function here, your F, it's not kx anymore. It's the weight of the bucket, plus the weight of the cable. And that's what I was showing up above here. So we have to come up with an equation for that. So I didn't really show you like what happens here, but it's the 500 that goes to 0. It's still 2 pounds per foot. So you have to come up with an equation for like this part on the right, which is really the weight of the cable here. And I think that's the most challenging part. So, well, how do I do that? Well, you do it this way. You've got 500, but it goes to 0. So you could just make an equation of a line, but x is the length that it's going up.
Mm-hmm.
So you generally, and this almost always works, you generally take this number and multiply it by the distance you're pulling at minus whatever variable you're using in this case.
Okay.
And you can see that at the top, when it goes up to 500, it's kind of backwards because it's going up instead of down.
Yeah.
But at 500, when you've pulled it 500 feet, this goes to 0, and this is always there. Okay. So once you come up with this, plus we'll distribute in 1,000 minus 2x, you get 1,800 minus 2x, and that's your f of x function. So when you come up with this, like it's not really like a difficult calculus problem anymore, because you're just integrating, as always. You're integrating your work is the integral of f times dx.
Mm-hmm.
So in this problem, it's the integral from 1,800 minus 2x dx. And then your bounds come from whatever they're asking you to do. Like part A could be to go halfway. What's the work required? Work to go halfway up. Okay. And we mentioned that, okay, it's 500 feet, but x equals 0 is down here, x equals 500 is up here.
Mm-hmm.
So in that case, you're integrating from 0 to halfway up, 250.
Okay.
A lot of these problems are sort of backwards conceptually. They're, you think x equals 0 is up here and 500 is down here, but and then you just integrate that. They could ask for the work on the second half. Okay.
So from 250 to 500?
250 to 500. And they might ask you to like make a decision, like, which one is more work? And you, it's not intuitive, so just work it out and see. And then a part C could be the entire work to go all the way up.
Okay.
From 0 to 500. And then another variation on this question that you might see is where you have to find the upper bound. So part D could be like, if the total, okay, like if a person can only exert 30,000 or 300, it's actually quite big, this problem, 300,000 foot-pounds of work, how far can they lift it? And in this case, they're giving you the answer, and they're saying, find that upper bound for us.
Okay.
But that's an exception. I mean, I wouldn't expect you to get anything like that. These are generally like the only two types of problems you see in this class. You see a spring problem, and then you see maybe a cable problem. When you take calculus 2, they do problems like water being pumped out of a tank, which it's really no different in terms of like how you do it, the setup. It's just coming up with the equation.
Okay. And so if the cable started at the top and was going down, with
would need
its,
you would need a different f function
okay.
because it basically negates everything we did unless you change this also.
Yeah.
So it could be both directions. Like you can negate your function and negate your bounds, and then it's the same. Or you can negate one of them and then keep one. You just got to be careful with it. Like if you get a negative answer, you probably either put the wrong bounds or put the wrong function with just a negative needed. Like it's a quick change if you get a negative number.
Okay. Okay.
All right. What I would recommend is not doing any more of these problems because you said it was probably just gonna be a small portion of your exam, and maybe focusing on the ones that you do want to work on. I see you said your Wi-Fi is having an issue. If you missed anything, let me know. We can. No, that was a
Oh,
while
it's
ago.
okay. I think it connected back in
Okay.
enough time. So.
All right. All right. So should we go to, for example, something in the calculator section, non-calculator?
Yeah, it doesn't, I think
Which
maybe,
is the least? Which do you feel the worst about? You know, which you say I don't feel good about this topic.
I think some of the, like finding, one of them was on the non-calculator when you're given velocity and you have to determine position like based on the graph.
Okay.
So something like that.
Okay. So let's just look at this together here. And I'm going to give you a nice velocity function because if you're just given a graph, then let me see here. Was it 1, 2, 3, 4, 5? Let's go there. Let's bounce. And I'll give you a little more here. Do you recall if the problems were sort of, I guess, nice for lack of a better, like straight lines?
Yeah, I think I
that,
think some of them would be, and then there's probably a couple that have a curve because some of them were given the graph and the area, and then we just have to determine position from that.
Yeah. Okay, so position is most generally the following. It is the initial position, and this needs to be given. You have no way to find it. Like they have to say in words, the car is there, or the car starts, 5 meters from home. Okay, plus the integral from, and then this, like these generally have to match.
Yeah.
And then it's 0 to x v of t dt. And what this right part means, area under the curve.
Okay.
Yeah. Okay. Now this could change. Like they could tell you at 4, 5, 6, 7, 8, 9. They could, and I don't know if you want to do this in this example. Let's not do that yet. Let's just do this one. So what is, and position, they wouldn't call it that. They would actually, let me not do that. Let me just move it. They would call it like S of t or G of t or something like that. And they would ask like, what is S of 4?
Okay.
Okay. And do you think you can calculate that for me from this picture? I guess
yeah. So
it's this is
would
5.
Okay, so it'd be the initial, which is 5. Is that, yeah, okay.
Yes.
And then the area of, is that like 4.5? The area?
It's the area is it's a triangle, so we would go just 1/2 5 times 4 for that part.
Oh, sorry, I added it by accident. Yeah, so 10.
Yes, so total is like 15, and they do want units, so 15 meters, because I specified that here. Okay, and then they could say, I mean, they probably ask you like S of 9 maybe, and you would do the same thing, but you'd have to add this other area. they would say, and so that would be like part B. Part C would be, when is the car furthest from home? But they wouldn't ask it this way, but that's what you think. They would say, where is maximum position?
Uh-huh.
Okay, and the max position occurs when you're only considering positive areas.
Okay.
Like this initial is 5. You add this one, that contributes positively. This one contributes positively. So it's
Mhm.
right there at 9.
Yeah.
Okay, and then they would say like, well, what is it?
Hmm.
And so that's where now I say, okay, well, let's calculate S of 9 if we needed to, and that's what it is.
Okay.
They could also ask you, and I'm sorry, please interrupt me if any of this is like unclear, if you actually want the
Yeah.
calculations. We're doing a very like, I don't know, high level macro view where I'm assuming you know how to do these calculations.
Yeah.
So they could also ask you, what is the acceleration from 0 to 4?
Hmm.
Okay, and this is nothing to do with like integrals. You like, since this is the velocity graph, they're literally asking like, what is the slope of the line from 0 to 4? What is the slope of
Hmm.
this line? And you would say minus 5/4.
Yeah.
Okay. They could also ask you questions, and you could tell me the statoscope, like where is the car speeding up and slowing down? This is kind of a first semester
No,
type.
yeah, I think they would ask that because I know in some of them, yeah, like in the calculator part, when we're given the velocity equation, we're supposed to like know when the particle's stopped or what
Yes.
direction it's moving and like where it is at a certain time.
Yeah. So the speeding up is when velocity is positive and acceleration is positive, or velocity is negative and acceleration is negative. And
Okay.
then slowing down is where they're not the same sign. Velocity is positive, but acceleration is negative. Velocity is negative, but acceleration is positive. And to answer these, we have to look at the graph and look at like slopes and position of the curve. So as a reminder here, let's go back. So from 0 to 4, the velocity is positive because it's above the x-axis,
Hmm.
but the acceleration is negative because the line has a
The
negative
slope
slope.
is negative.
So in
Okay.
this case, it's slowing down,
Yeah.
which is kind of odd. I mean, it doesn't like intuitively make sense, but if you just apply the definition, you're like, okay, that's what it says.
Hmm.
From 4 to 6, the velocity is positive,
And
and
acceleration is positive.
so it's speeding up.
Yeah.
Okay. Here from 6 to 8, the velocity is 2 and the acceleration is 0. So
Hmm.
it's constant velocity.
Okay.
8 to 9 is the same as 0 to 4. It's
Hmm.
velocity is positive, acceleration is negative, so it's slowing down. From 9 to 10, though, the velocity is now negative and the acceleration is negative, so it's speeding up.
Okay.
And you have to apply those rules, as appropriate for this problem. Okay, so I'm going to grab this graph and just draw a variation on the same question. Is anything you want me to cover again on the kind of the last example?
Yeah, I think that was, can we do one with like more of a curve?
That you can't find, yeah, I mean, I can make these curves, but you can't actually find areas in that case. But
Okay.
we can use we can do something else. We can go something like that, maybe. Okay, so the position function this time is S of, all right, so S of t is is S of 4 plus the integral from 4 to x v of t dt. So this time they're like telling you like, this is your starting point.
Okay.
Okay. And I'm just going to give you some areas here because we actually do need to know these. I'm going to say this is 10, this
Mhm.
is 3, this is 4, and this one is 2.
Okay.
Okay. And somewhere they tell you that S of 4 equals 1.
Okay.
Okay. So if I asked you for, like, question A could literally be, what is S of 4?
Mhm.
They're giving it to you right there, but the way you would write is 1 plus the integral 4 to 4 v of t dt, and because these have the same bounds, this is 0.
Yeah.
So it's just 1.
Okay.
Part B would be to find S of 0. So S of 0 is S of 4 plus integral 4 to 0 v of t dt.
Okay.
Okay, so it's the same as the previous problem, except you now have to do the integral. But like you said, you want something with a curve, but you can't, unless I give you straight lines, you can't actually calculate it. So I have to give you the area.
Yeah. So what if I'm given the area and the velocity equation? Can
If
you
you're gonna,
show one where you would like then find position?
yeah, we would have to integrate. Let's finish up just a couple more parts of this, and then
Yeah.
we'll go right to that.
Okay.
Because this is important here, is that when you're going backwards like this, the
Uh-huh.
area above the curve is negative. So this is minus 10,
Okay.
which is minus 9, which is a little weird, but that's what it is. And then this is the real question I would ask is where is S of t a max?
Mhm.
Okay. And the way you attack a problem like this where it says maximum is you have to go to that starting point. You have to go to wherever you
Okay.
started. And okay, and you say that's 1. And if I
Mhm.
go forward, that negates it. So
Yeah.
it's 1 minus 3 if I get to there. But then I can add 4.
Mhm.
So it's 1 minus 3 plus 4, which gets you to 2.
Mhm.
Okay. And then if I go all the way here, this is now negative 2. So
Yeah.
it's 1 minus 3 plus 4 minus 2. I'm sorry, 1 minus 3 plus 4 minus 2. So it ends up being 0. So you basically need to figure out at all these sort of breakpoints, you need to figure out like, okay, well, S of 4 is this,
Mhm.
S of, which we said is 1, S of 6, let me get the points. And then S of 6 is 1 minus 3. S of 8 was 1 minus 3 plus 4. And then S
Mhm.
of 10 is 1 minus 3 plus 4 minus 2. And we get these numbers. So 1, negative 2, positive 2, and then what is this last one here? 0. And you just literally look like, which one's the max? That's the max, and that's the min.
Okay.
And you do those at each of these sort of like break
Major
position.
points. Okay.
Yes. Okay. All right. Now, the question you really want to answer is truly a calculator problem. They would just tell you v of t equals I don't know, 8 minus t cosine of I don't know, 3 to the t.
Mhm.
And let me just graph this and see if this is even reasonable because I just made this up. And
Okay.
I don't know. 8 minus x cosine. But yeah, I remember you had something like this on your review. Let's go from 0. One's kind of boring. Let's go 1. Let's go 2. 2's too far. 0.6. Okay. All right. And would you be comfortable graphing this on your own if you had to?
Um, yeah, I think I
In
would
the
probably just
in the
make like a
calculator?
table. Oh,
This
well,
is
okay. It's just like
is it, do you want a non-calculator problem that we would do like this?
yeah,
I
sorry.
see. I see. Yeah, so we won't do this one. This is a good calculator problem if you
Okay.
want to look at it later. All right, let me pick one of those up. um And go there. All right, so this one, let me not make it too difficult here. So this one would be v of t equals minus x squared plus 4x minus 3. I guess these would be t's. Okay, and it would say
Okay.
from 0 less than or equal to t less than or equal to 4.
Mm-hmm.
Okay, and if you have a rough idea of the shape of this, you probably know that it goes up and goes down because it's a negative out in front.
Yeah.
So the very first thing you would want to do here is to set v of t equal to 0.
Okay.
So you got to set minus t squared plus 4t minus 3 equal to 0. And I would factor out the negative. So you get t squared minus 4t plus 3 equals 0.
Mm-hmm.
And you get t minus 3, t minus 1 equals 0. So t equals 3, t equals 1.
Okay.
All right, so then I could ask you all this kind of all the same questions. I could say, assume s of 0 equals 2, and I could
Mm-hmm.
say, what is s of 1? And what that is it's s of 0 plus the integral from 0 to
To
x
1.
v of t dt, but this time
Okay.
you actually have a v of t.
Yeah.
Your v of t is this thing up here, is this
Okay.
one right here, and that's a nice, relatively speaking. It's you have it, so you can
Mm-hmm.
just you can say, okay, it's 2 plus the integral from 0, but in this time we want it at 1, so 0 to 1
Okay.
minus t squared plus 4t, what is it,
-3.
minus 3 dt. Okay. Now, do you expect the integral to be positive or negative? And we can go back to the graph and look.
Negative.
Yeah, because it's all this area right here.
Okay.
Okay. So do you want us to do this integral?
No, I just wanted to
Okay.
like see more of the setup of it.
Okay. Great. So the another question that I could ask you here is I could say, what is the total displacement from 0 to 4?
Okay.
And total displacement in this case would be 2 plus the integral from 0
To
to
4.
4 v of t dt.
Okay.
But in truth, you're probably not going to get that first. What's probably going to ask first is going to say, what is the total distance?
Mm-hmm. And that's just the integral.
Well, it's the
Right?
integral, but broken up. It's 2 plus the integral from, well, let me not put that there. It's going to be the integral from 0 to 1 v of t
Mm-hmm.
dt, the integral from 1 to 3 v of t dt,
And
and the
then,
integral from 3 to 4 v of t
yeah.
dt. And you have to figure out, well, is it positive or negative in each region? So you would go back here and say, oh, from 0 to 1, it's negative, so from a negative there. From
Mm-hmm.
1 to 3, it's positive, and from 3 to 4, it's negative.
Okay.
So that you would negate that, you would add that, negate that, and then you have a 2 there. Because the total distance is like when you drive your car, and it's the odometer is always increasing, whereas the displacement is the difference from where you started.
Uh-huh.
So like if you leave your house and come back, your displacement is 0, but your
0, but
distance is whatever.
still there. Yeah.
Yes. And so the that's where these signs come in, because if you just straight do it, you'll get a number and think you're okay, because there's probably a little more area above the axis than below, so you might think that you
Mm-hmm.
worked it out correctly. The next question that could be asked is, it says, where is position min/max? Okay, and to do either of these types, you have to look at each of these sort of points
Mhm.
and see what's going on. So it's like S of 0, you got to figure out S of 1, S of 3, and S of 4, because these are starting point, ending point, and then these are
And
crossing points.
yeah.
And so the numbers you get over here, you know, what there'll be one that's bigger than the other, hopefully, and one that's smaller than the other, hopefully. And that will give you your min max.
Okay.
So like this is 2, just 2. This is 2 plus integral 0 to 1. This is 2 plus integral 0 to 3. This is 2 plus integral 0 to 4. So notice when I ask about position, it's more like asking about distance. I'm not asking for displacement.
Okay.
All right, I'm gonna just I've got to check on something for 30 seconds. I'll be right back and we can continue with whatever you want to go for the next problem.
Okay. Sounds good.
All right, Naomi, I'm back. What would you like for us to look at next?
I think maybe um maybe another either I want to do one more like revolving one, kind of like there was that one with the eclipse in the practice thing.
Okay.
So just kind of like finding volume of a revolving region,
All
and
right.
then maybe one more with like net change, kind of like, you know, like the number of people going in an escalator, like that type of question.
Okay. Sounds good. We can definitely do that. So let's how do we want to do this here? I'm just trying to find some interesting functions here. Let me change this one up a little bit. That doesn't help all that much, but we'll do that. So let's say we want to revolve the area between y equals 1 over x and y equals x squared from 1 to 2.
Okay.
This is x equals 1. So we can do this. You know, your review thing said you've got to first find area between. And that's pretty reasonable here. So if you don't know what these graphs look like, you may want to sketch, you know, a brief graph, like one goes like this and the other goes like this, and they hit somewhere. So if they hit more than once, you probably have to set them equal to each other.
Okay.
And if we just do that here, I think you'll see this. It's not too bad here. Is that 1 equals x cubed, so x equals 1. They intersect when x is 1, and then to find the y value, you put it back into one equation or the other, and you get 1. So we're looking actually, if we want to make like a better graph, we're looking at, well, that was not better. I'm going to call this 1, 1 here. They hit there, and you can see the x squared goes up like that, and the 1 over x is down there, and that tells you that the top to bottom. So that'll be a 2. So you're integrating from 1 to 2. Top is x squared minus 1 over x dx.
Okay.
Okay, and you get a number. The one on the right is your natural log absolute value of x, and as a reminder, natural log of 1 equals 0. They do expect you to simplify that.
Okay.
Okay, so the next thing we can do is maybe do some cross sections.
Mm-hmm.
We saw that's probably covered. So let's say the cross sections are circles with diameters equal to the distance between the two graphs.
Okay.
Somehow it would express that. So
Yeah.
the like, and what I recommend is drawing the cross section here like that and being like, okay, what is this? The diameter here is top minus bottom.
Mm-hmm.
And it's the same as this. It's x squared minus 1 over x. Okay. And then saying, okay, well, I need the area of a circle. The area of a circle is pi r squared.
Mm-hmm.
In this case, your r is half of this.
Yeah.
It's 1/2 x squared minus 1 over x squared.
Mm-hmm.
Okay. And then you're integrating still from 1 to 2. This is now your volume. It's your area function, which you just found, 1/2 x squared minus 1 over x squared dx.
Okay.
And this is due, this, like, just to be clear, like, this is totally doable. Like, the 1/2 squared gives you pi over 4.
Mm-hmm.
Okay. And then this right in here, I mean, it looks bad, but it's when you multiply these, if you remember your a minus b squared, when you multiply these, you get x, negative x, and then you double it, you get minus 2x minus 1 over x squared. It's just a power rule integral. So it feels like it's bad, but it's
Not really.
not really. It's doable. I mean, wouldn't give you like 10 of these. I'd give you one and give you 10 minutes to figure out all these different parts, or more time than that. So that's cross sections.
Okay.
Then we can do an x-axis integral.
Okay.
So it's still top minus bottom again, though. Top minus bottom. It's a pi r squared. So it's integral from 1 to 2 because we specified that pi, and then your top this time is the x squared minus 1 over x squared. This is not, oh, it is a disk. Oops. Or it is a washer. Let me take that back. So let me get the graph again of this. Didn't do a good job. So how would you know this? How would you know this? I guess, and this would not be a calculator problem.
Yeah, I mean, there's some that are calculated and some that are not, but it would be a washer because it's like just kind of the shape of it, right? Like the inside is.
It's because there's a gap between them. There's your big R, and then there's your little r.
Okay.
There. And you know, it's not, I was about to do a disk, but that would be completely wrong. So the integral is from 1 to 2, but this time it's pi and then big R squared minus little r squared dx.
Okay.
And it's,
so big R is always the top curve if it's the x-axis.
yes,
like
top minus bottom.
X.
Yes.
Oh, and then Y, it's right minus left.
Right minus left. Yeah. This would not be, this wouldn't be a good one for us to do on the Y, so I can make one up that's better. But the the R is in this case it's x squared minus 1 over x squared dx. And again, it's totally reasonable to do this by hand. It's not an impossibility because they're just powers.
Okay.
All right, and I think that's it. I think you asked for area, cross sections, and volume. We can do some y-axis now if you would like.
Yeah, maybe a y-axis and then a net change, and that I think is all I had major questions about.
Okay, sounds good.
Thank you.
I'm trying to come up with here that's something more reasonable, but I'm not able to do that. Okay, yeah, so this one here. So we have y equals 2x and y equals 5 square root of x. And it
Okay.
would say to find the area between would be
Mhm.
part A. And this one you can do actually the standard way. You can just do a top minus bottom if you wanted. All right.
Okay.
But then part B, which is what you care about, is we're going to revolve around the y-axis this time.
Okay.
Okay. And there's many problems now with this. The first is that you actually don't have any idea where they intersect. Okay.
Mhm.
So you would set 2x equal to 5 square root of x. And this may or may not be a comfortable solving thing, but you could square both sides like that, and then move everything to one side, factor out an x, and you would get x equals 0, x equals, oh, I'm sorry, this is 25x, 25 over 4, which is 6.25. So this doesn't look great, but it's it's reasonable. I mean, like you can
Mhm.
do this, okay?
Yeah.
So, but the problem is when you need y-axis, you actually don't need either of these. You need the y values. So you have to take both of these numbers and put them back into the other one equation or the other.
Okay.
Okay. So if you had a choice, you put them back into this easier one. So y
Mhm.
equals 2 times 0 is 0. That's great. So that tells you 0, 0 is an intersection point. And then 2 times 25 over 4, 25 over 4, which is 25 over 2, which is 12.5.
Okay.
Not great, but maybe just set these up. Who
Yeah.
knows? Who knows? So do you have any idea like what these graphs look like? Just even if it's just 2x goes up,
Mhm.
root x does actually this. I know that's not
Yeah.
okay. But
That kind of stops it.
if you weren't sure, if you had no idea, you could choose a number between the bounds. You could choose a y. You could choose a number between the y's here. So like you could go y equals 4 because the square root of that's, well,
Mhm.
actually you don't even need that, but you could then figure out which x was right or left. So to do that, you really need to solve both of these for x. So x equals 1/2 y. And then on the other one, it's x equals y squared over 25. So if you put 4 in, you get x equals 1/2 of 4, x equals 4 squared over 25. And you would say, okay, this one is more to the right.
Mhm.
X equals 2 is more to the right than the 16 over 25, which is the left.
Okay.
Because you need to integrate right
From right
minus
minus
left.
left.
And if you don't have a calculator, and if you guess wrong, you'll get a negative answer, and then you got to switch everything
Okay.
when you're doing that.
Okay. Cool. Makes
So
sense.
that would, so let me just finish this off here. It'd be from 0 to 12.5. That's the y value.
Mhm.
This is a washer problem because you don't have you do have a gap between there. So
Mhm.
your right function is this 1/2 y squared minus y squared over 25 squared dy.
Okay.
And if you haven't noticed this by now, the higher the power, it
Mhm.
tends to go on the right part
Okay.
over here because it contributes when you put the bounds in, it gives you a smaller number for it.
Uh-huh.
All right, so you said net change. Okay, so if I tell you the flow in to something is 2x, and the flow out is I don't know, minus x squared minus square root of x.
Mhm.
And I tell you that, d of 0 is 500.
Okay.
There's 500 people or 500 things starting.
Mhm.
So your net change is always the amount going in minus the amount going out, but you always have your starting amount. So your net in this case would be d0 plus integral. And we'll just say this goes from 0 to 4 hours, 2x dx
Minus.
minus the integral, minus x squared minus square root of x. Actually, I these should be positive because that won't actually work, from 0 to 4 dx.
Okay.
All right, and then that's the net change. Now they could also just ask you about when is the net change the greatest,
Mhm.
and they're asking you to like look at the in minus out and create a like either look at that function or take its derivative to find that. Let me just see if I can make that work real quick. See if it actually looks, and you get, actually that does look okay. So let me go.
So is that when you like set them equal and solve for?
So if they want to know where where is so it has to be in context. So it'd be like, where is the min or the max?
Uh-huh.
Okay, they're actually asking you to look at just the net change, just the 2x minus x squared plus the square root of x,
Mhm.
and figure out like graphically where is it a max. So let me show you that real quick on a graph, so you can see that it actually does have one that you could find. That this is the graph. So this is your max, and this is your min. Forget about this over here on the right for the moment, because I would change the bounds to like 0 to 1 or something.
Yeah.
But it's looking at this one here to do now, because of where these cross.
Mhm.
You could be asked to do something like let's call that 0.4, and that's 1. You could be asked to find d of 0.4 and d of 1 and make some inference about those points like we were doing earlier.
Okay.
You'd actually have to get those numbers though, the one at 0.4 and then the one at 1.
And so what equation would you plug that into? Just the
It's d of 0 plus the
just that
integral
one? Okay.
0 to 0.4, and then your change, in minus out. And
Okay.
this would be from 0 to 1 in minus out. All right, so we do have to stop here. This takes us to the end of our lesson for today. If you understood all this, I think you're in great shape. I'll try and upload the YouTube screen share here relatively quickly, in case you want to look at it today. But I'll send you the notes out shortly, and I'll see you next time.
Okay. Thank you.
Have a great day. Bye now.
You too. Bye.